Welcome to our next video in the series on stress and strain. In the previous one we looked at stress and you learned that stress was load over area, and we didn't do much about strain other than introduce it. Now we're going to focus a little bit more on the strain aspect. Now if we have a look over here at the first section, we're going to look at mild steel and how it behaves when it's loaded in tension. Now the reason for mild steel is many designs that you're going to work on will use mild steel, since it's a very common material out there. So if we dive straight in and we have a look at this little graph where we've plotted stress, which is a known quantity for us already, but we plot it now against strain. Now cast your minds back and think what strain was. Strain was change in length over original length. Remember, it was a unitless ratio. So assuming we do a test on a specimen, and you were to plot values of stress versus strain, you would pick up some interesting trends. That being that initially, from the starting point of the test, when the load was zero and hence the stress was zero, slowly as you increased the load and hence the stress and hence the strain, you would find a straight line initially. Okay, now here are the important points. That straight piece would stop being straight at a point called the limit of proportionality. We're going to go into each of these definitions below, and we're also going to deal with a quantity called the elastic limit, the yield point, and a few other numbers we're going to look at. So let's take them step by step, and maybe at this point it would be a good idea to go and watch a little video, which there are many on the internet. Here's one over here. So what I suggest you do is go and have a look at this one and then come back to this video once you've watched it. That'll give you a little bit of insight into what it is we're doing in a typical materials test. Right, so you watch the little video and we're going to go straight into the first aspect, which is elastic range. Now our graph can be divided up into an elastic portion called the elastic range and a plastic range. So the elastic range starts at the origin, and as we said earlier, it ends at the limit of proportionality. So here we go. This is the straight line portion of the graph between the origin and the limit of proportionality. Now here's the important part. No permanent deformation occurs in this region, and once the load is removed, the steel will return to its original dimension. Okay, so that's important in a design. We'll discuss that a little bit later on again, but basically, if we don't want our component to be permanently harmed after applying a load to it, we had better stay in the elastic range. And in other words, in that area called the elastic range, our piece of steel behaves in a perfectly elastic manner, much like an elastic band. If you take an elastic band and stretch it between two fingers, provided you don't go overboard and apply way too much load and snap it, it will always return to its original length and act like in a perfectly elastic fashion. Okay, so that's the elastic range. The plastic range is where the permanent deformation occurs. So that is this curved portion of the graph. And it starts at the elastic limit and it goes all the way to the point of fracture or failure. Now here, permanent deformation occurs. And if at any point we were to remove the load, the steel would be permanently deformed. It would have become slightly longer. Okay, so the limit of proportionality, we've already said this. This is the point where the straight line ends. In other words, up to this point, the ratio of stress to strain is a constant. Beyond this point, it is not. Okay, now I want you to remember this ratio of stress to strain. We're going to do that again in a little while. Elastic limit. Now this is a stress value, and it's the one that occurs at the limit of proportionality. So in other words, it is the stress that happened when your graph was at that point called the limit of proportionality. In other words, this is the highest stress in the material, the highest stress the material can endure without sustaining permanent deformation. Okay, straight on to the yield point. This is something we're going to be hearing a lot of, is yield stress and yield point. This is the point where the steel suddenly yields or stretches with little or no additional load. Remember that, with little or no additional load. The stress value corresponding to this point is known as the yield stress. You're going to use this a lot in your designs. Okay, one more is the ultimate stress. Let's go back to the graph. Have a look where ultimate stress is. This is where the graph peaks. And remember, the value that is peaking is the stress value. Okay, so back to the definition. What does it mean? It says the ultimate stress is simply the highest stress value recorded during a tensile test. No need to make it more complicated than that. It's simply the highest value. Now, that little video that you watched, you saw the necking of the material during the test. Okay, so let's read this. When the steel is close to failure, it starts to neck. This is a reduction in cross-sectional area just before failure and accounts for the shape of the graph past the ultimate stress point where strain continues to rise but stress reduces. Alright, so that explains this dip in the graph that we have over here. Okay, it's a little bit academic because we certainly are not going to be designing components that operate in this area, but it's important that we understand what it is. Okay, one more for this page. The stress at failure. You saw the component fail in that little video, and at that point of failure, this is the failure load divided by the cross-sectional area at failure. The latter area would be less than the original area due to necking. Okay, so what that means in simple terms is, when the component failed, what was the stress at that instant? How would you find it? Well, you'd need to know the load at failure and the cross-sectional area at failure. Remember that that cross-sectional area is reduced from the original area. So to summarize, let's look at the graph one last time. It's a graph of stress plotted against strain. Both quantities you should be comfortable with by now. We start off with a perfectly straight line portion. Remember that in that area the component is not deformed permanently. It would spring back to its original dimension if you were to stop the test at any point there. After that, we have the limit of proportionality, the elastic limit, and then yield. Remember what yield was? Yield was where you had sudden increase in strain with little increase in stress. Okay, after that we went into this curved portion of the plastic range, and the stress value increased, and it eventually reached a peak. Remember, the peak is called the ultimate stress. And then after that, with the necking and the reduction in area, we had this drop of stress, and finally failure occurred over there. Now, if you're designing a component and you don't wish the component to fail prematurely, and you wish to use the component a number of times, which in most cases would be what you want to do, then you would try and keep your stress way below the ultimate stress. And you would want to keep the stress at what we call a working stress. Now, to achieve that in an orderly fashion, we come up with this factor of safety. Now, the factor of safety is simply the ultimate stress divided by this working stress that you are going to use in your designs. So here's the wording. In virtually all mechanical designs, machine components are planned to be used over and over, and it is desired to make them last as long as possible. To achieve this, one cannot allow their stress to enter the plastic range, as they would after one load application be damaged. The stress must therefore be maintained well within the elastic range. Remember, that's the straight line portion. It is convenient, however, to relate this safer working stress to the ultimate stress via a factor known as the factor of safety. So if you know where the material breaks, in other words, at what stress the material breaks, and you know how safe you wish to make your design, you can easily calculate the stress that you are going to use and hence use in your calculations. So if we go back to our stress-strain graph, remember ultimate stress was the highest value occurring during a test, that's over here, but we said we want to work well within this straight line portion. So you can see that the working stress is significantly less than the ultimate stress by a certain factor. Now, there are no hard and fast rules on what safety factor to use where, but here is a very, very loose and broad guide of safety factors used in industry, and you'll see that safety critical items have the highest factors of safety. And where cost is involved, obviously that's involved everywhere, but when cost is a big deciding factor in what the design might look like, designers might be forced to err downwards and keep the safety factor as low as possible to keep the cost of manufacture low. Another industry that would require quite low safety factors, believe it or not, is ones where weight is a big aspect. For example, aircraft components. You would think that they would be some of the safest ones out there with a higher safety factor, but that's not the case, because you can't have aircraft that are too heavy, they won't get off the ground. So oddly enough, aircraft have a safety factor between 1.5 and 2.5, whereas something like shafts in machines can have as high as 10 to 12. Let's look at some others. Lifting hooks, you can imagine the hook on a crane, you don't want that failing, and 8 or 9 would be a good safety factor. Weight might not be a big issue there. So you can have a look through this list and see what typical safety factors are used. Right, so we've looked at the graph. Now, how can that graph help us in everyday design work? Well, here we go. This is the useful part. Let's talk about Hooke's law and this modulus of elasticity. And remember, earlier I spoke about a ratio of stress to strain and the fact that it was a constant in the straight line portion of the graph. Well, Hooke's law states exactly that. He states that within the elastic range of any material, the ratio of stress to strain is always a constant. Okay, remember that's the straight line portion. This constant is known as the modulus of elasticity and is denoted by the letter E. Now you'll find E in many design aspects in mechanical engineering. And there it is. E is stress over strain. Okay, but now let's cast our minds back to what stress was. Stress was load over area, and strain was change in length over original length, both well known to you. So let's dive in and substitute those, P over A, load over area, for stress, and let's substitute change in length over original length for strain. And we end up with P over A upon lowercase e over L. And if we rearrange that a little bit, we can then have E equal to PL over EA. And that's a very useful formula, as you'll see in a moment, when we want to work out, for example, a change in length for a given load. And provided we know the E value for that material, and we are in fact working in the elastic range, we can use this formula quickly and easily to find out, for example, how much a component would extend under load. Now, before we dive into our first worked example, let's finish off by talking about ductile and brittle materials. These are both words I'm sure you've heard somewhere along the line, but let's expand a bit on those terms. Ductile materials have the ability to be hammered thin or stretched into wire without breaking. Okay, and here are some examples. Mild steel would be considered ductile, aluminium as well, copper, rubber, and most plastics. Okay, so if you were to consider possibly a wire nail, one that you typically would knock into wood with a hammer, that would be made of a ductile material and more than likely was drawn into wire, the end sharpened, and it was formed into a nail, for example. So the mild steel that you're going to use in many of your designs, probably the chair that you're sitting on has got mild steel in it, aluminium window frames are all around you, copper you see here and there, rubber you're familiar with, I'm sure, and obviously lots of plastic materials are quite elastic and have this ductile behavior. Brittle materials, on the other hand, are quite the opposite, and straight away let's take some examples. Ice would be considered brittle. Many stones, I think all stones could be considered brittle as well. Ceramics, if you drop a plate or a cup, it shatters. And when we get back into steels, a steel such as cast iron displays brittle properties. Okay, so the definition or the little explanation says brittle materials, when subjected to stress, break with little elastic deformation. and without significant plastic deformation. Okay, so the graph is going to look very different to the one that we studied earlier. It will be steep and won't display all the long plastic region that we had in that example. Brittle materials also absorb relatively little energy prior to fracture, and fracture may be accompanied by a snapping sound. Okay, so now we're going to go on and do a worked example. And in this worked example, it says it was found that a load of 120 kilonewtons produced an extension of 4,656 millimeters on a mild steel bar 4 meters long and 25 millimeters diameter. You must find, firstly, the Young's modulus for the material. Remember, that is E. Okay, so that's A. And then the B part, the minimum diameter of a bar of the same material 5 meters long, supporting the same load if the extension is limited to 3 millimeters and the stress to 195 megapascals. So what they're saying is find the Young's modulus and then do a little calculation, a little design basically, where your two constraints are given and you must work out the minimum diameter of the bar. Okay, so what I propose you do is stop the video now, work that out, and then once you've attempted it, restart the video and have a look at the solution. So let's look at the first part. Remember what they said, 120 kilonewtons on a 4 meter long bar produced extension of 4,656 millimeters, and the bar had a diameter of 25 millimeters. Now our little formula for E says PL over EA. That is load times length over extension times area. So here we go, 120 kilonewtons times the 4 meters. Remember that we go in with units in the base SI units. That's how they go in, so that's meters. At the bottom, 4,656 times 10 to the minus 3. That's a convenient way of expressing millimeters as meters, or converting millimeters to meters. There we go. And the area, the cross-sectional area of the 25 millimeter bar would be pi over 4 times d squared. Once again, expressing the dimension in meters. Plug that into your calculator and you'll get 210 times 10 to the 9, which is 210 gigapascals. Remember to use the E and G button on your calculator. So now we know that the E value for this particular material is 210 gigapascals. And then they gave you two design parameters. First, they said the extension may not exceed 3 millimeters. So make a heading and say what your design constraint is you're dealing with. Take your formula, E equals PL over EA. And remember that E is now known to us as 210 gigapascals. The load, they said, was still unchanged at 120 kilonewtons. But the bar was 5 meters long, and it was not allowed to extend more than 3 millimeters. So there goes the 3 millimeters in there. You could also have written that as 3 times 10 to the minus 3, whatever you prefer. And the area is what we are looking for, or rather the diameter is what we're looking for. So pi over 4 with d being the unknown. Okay, so we're going to solve for d, the diameter, and we find that 34,823 millimeters is the diameter that we require so that the extension is 3 millimeters. So that's the one half of the design complete. The other half said, whilst all this is happening, we are not allowed to have the stress exceed 195 megapascals. Now remember what stress was. Stress was load over area, or load is stress times area. And this 120 kilonewtons must not exceed 195 megapascals of stress. So we simply solve for the diameter, and we find that the diameter is 27,99 millimeters. Okay, so which one are we going to use? 34,8 or 27,99 millimeters? Well, let's look at the question once more. What did they want to know? The minimum diameter of a bar of the same material. So if we go back to those two answers, if we were to use the lesser at 27,99, we would not satisfy the first design requirement. So we can't go below 34,823 millimeters, otherwise we won't satisfy both design requirements. Okay, so go through all of this and make your own notes, and in the next video we're going to go through the tutorial solutions. Thank you for watching.